Okay, today is what is today? March 9, happy Wednesday. The most recent take-home quiz is due right now at this moment. Throw it in the folder in whatever state it is in. This is when it is due. You are also currently working on project number 4. That's the gamma function project. That one is going to be due on Friday, and a lot of folks I know are making very good progress on that, so keep it up. And keep in mind that, well, we'll say this in a second on the packet. What I've highlighted up here is, the next couple of weeks for us, couple weeks plus. This is our next major theme of the course is applications of the integral. All of these things highlighted here are going to be applications of the integral. We'll spend a few days talking about areas and volumes. Then we'll do some physics stuff with density, more physics stuff with work. We'll do a day on economics and another day on probability. So all of the things in the next few weeks are applications of the integral, and they all hinge on the stuff that we're going to do today. Any questions on the calendar?
So not so much improper stuff.
Right, we're leaving the improper integrals behind. Yeah, they will come back after the second test. Okay. All right, so here we are at the top of page 30, daily summary. Today we learn how to measure area or volume of an irregularly shaped object by slicing the object up into easy to measure pieces. And like I said, all of the applications that are coming hinge on this idea from today, this idea of slicing that we're going to talk about. Just a note in number 1 about the Gamma project. It says problems 5 and 8 from the Gamma project are particularly tricky. You can find a YouTube video of Caitlin going through and giving very detailed hints on those 2 problems. There's a link here, but that's probably not worth writing down. You can search for that particular title on YouTube. Easiest would just be to go into Moodle and you'll find direct links to a video of hers and also a video of mine, all right? But I strongly encourage folks to watch that as they work on problems 5 and 8. Okay, number 2. Recall our definition of the area under a curve was this long thing here. Let's make sure we understand the pieces. So this delta t was supposed to remind us, I'll just draw a quick picture over here, which I will erase. But we'd be looking for an area and we would say, hey, we're going to approximate this curvy area with rectangles, and we're just going to draw lots of rectangles in there. And if we use infinitely many rectangles, we'll get the exact area. And we would typically call the width of that rectangle delta t or delta x. And then the height of the rectangle would be f of something, t sub I maybe. And so that's all that's going on up here. Delta t times the first height, delta t times the second, times the second height, delta t times the last height. So everybody buy that that thing is just the sum of the areas of a bunch of rectangles? And like I said, if we let the number of rectangles go to infinity, we're going to define that to be the exact area. It's written slightly differently here. Having the number of rectangles go to infinity is kind of equivalent to letting the widths get infinitely close to 0, right? And that's what the limit there says. Okay, and then we just defined this crazy symbol right here to be that limit, to be the exact area. Okay, so we can convert certain Riemann sums, that was the left-hand side of this equation, into corresponding integrals, and this is something we're going to be doing repeatedly over the next few weeks. We'll start with number 1. Let's find the areas of these figures, number 3. Let's find the areas of these figures by slicing them up into rectangles, writing a Riemann sum, and then rewriting it as a definite integral. This figure here and many other figures in this packet are scanned from your textbook. So we're going to find the area of this triangle. What is the area of that triangle? 9, right? Half the base times the height. Okay, we're going to get the answer of 9 in a far more complex way than half the base times the height. But the idea is that the method we're going to use here will give us the ability to find areas of things much more complicated than this triangle. So here we go. We're going to take this triangle and we're going to slice it up into things that are approximately rectangular, like that thin little vertical thing right there. It's not quite a rectangle, but it's pretty close. And the thinner you get, maybe the closer it would be to being a rectangle. And so here's what we're going to do. We're going to write this. The area of one slice, and that little rectangle is what I'm going to call a slice, is equal to, so we know the formula for the area of a rectangle, it's base times height. What's the base symbolized as here? Delta x, so there's the base, times the height. I don't have a name for the height, I'm just going to call it y. And we've got the area of one slice. Now it turns out whatever letter is sitting next to that delta is the only letter that's allowed to be in this expression. So the fact that that's a y is very problematic for us. We need it to be x's, something with x in it. So let's take a look at this and remind ourselves of a little bit of high school geometry. We've got two triangles here. There's the big one, and then there's this little guy here. Right, the entire thing in that one. Anybody remember the name for the relationship between the little triangle and the whole thing? They are similar triangles, yes? And we remember the relationship between corresponding sides of similar triangles? They're in the same ratio, right? This is geometry facts. So if we take a look at the ratio of y, which is the height of the small triangle, to the height of the big triangle is 3, then it better be the same ratio as, okay, now name another little side of the little triangle, x, to the corresponding side of the big triangle, 6. Everybody buy that from geometry class? Okay, you could solve this equation for either x or y, but remember what I said. The goal is to have only the variable that is sitting next to the delta. So I want to get rid of the y. So I'm going to solve this equation for y so I can substitute it over there. So multiply by 3. And then we'll reduce. Y is equal to x over 2. Yeah? And so then we come back up here and we say it's delta x times, and now instead of y, x over 2. Everybody buy that? And now I'm breathing easier because the letter right after the delta is the only letter that appears anywhere in that expression. It's only x's right now. Okay, so that thing right there is the area of one little slice, or it's approximately. Maybe I should actually change. Ben, you had asked me earlier this semester about using equals when it didn't really seem like in the limit it should be equal. So I'm gonna use an approximately here because it's not really a rectangle, right? That little slice is not a rectangle, but it's close. So the area of one slice is approximately that. So that means that the area of all the slices is approximately, well, I'm just going to add up expressions of the form, this thing we've just calculated here. So it's really just delta x times x over 2, but we're just going to add these guys up. And you guys remember the fancy Greek symbol for adding a lot of things, that, right, that sigma. So it's just that. I'm going to put something here in red, which is a technicality. I don't need it from you. But typically you would number the x's, right? Like x1 and x2 and x3, just like on the top of the page, that crazy formula with the t's in it has a t1 and a t2 and a t3. So technically we're numbering these guys. Here's another technicality in red, which I do not need from you. So the red stuff is optional. I'm just filling it in so you see that it's not just a matter of plopping a sigma in front. It's really just like numbering everything and then saying, hey, we're adding all these up. So that would be the sum of all of the rectangular slices. And if I put a limit in the front of that thing, summation of delta x times x over 2, and we send the number of rectangles to infinity, then we're saying that's the exact area, right? That's what it means. That's what we mean by the exact area. So we'll say the actual area here equals, not just approximate anymore, and I see this crazy summation here, and I say, hey, this looks just like an integral. We're going to change that into an integral. So let's just start copying stuff over. The delta x inside of the sigma becomes what symbol in the integral? It becomes a dx. I'm going to highlight corresponding things here. So that guy became that. The x over 2, it just gets copied. I'm going to put my not mandatory I there to just show you that it changed a little bit, right? Technically there was an I and then we drop it, but I don't need you to even put it in the first place. Yeah, Rob? Yeah, there is. It's an approximation if you're just adding up your rectangles areas. But if you send the limit, if you send n to infinity in the limit, then well, it's our definition for the area, and the errors that you've introduced by using rectangles become smaller and smaller to the point that they're insignificant. Yeah, disappears. That sigma becomes what symbol over here? Integral. There you go. And it might be something you've seen before, but I mean, the sigma is what letter in Greek? S. And this integral looks to me like an elongated S. It is not a coincidence. S and S. Okay, so we've converted that crazy summation with an infinite limit into it into an integral. The only thing we need to do is account for the values. Think about this slice sweeping from left to right. How much is x at the far right? 0. And how much is x at the far left? 6. So this is just an integral from 0 to 6. And we can do this integral a whole lot easier than we could find that infinite limit of things over there. So we'll do the integral. Let's see, x becomes x squared over 2, but there was a 2 there before. So x squared over 4 between 0 and 6. It's 9. Don't ruin it. Big surprise, the big reveal. Okay, so the answer, of course, is 9. Same thing that we got before by using the much simpler half base times height. I want one more thing I just want to make sure we take away from this. I really like the idea of thinking about that slice sweeping through, sweeping out the entire area from left to right or right to left, right? And that dx to me right here indicates a sweeping motion, so left to right sweeping until we shade in the entire area. Okay, that was so much fun in 2D. Let's go down to number 4 and do something in 3D. We're going to use the same Riemann idea to find the volume of this solid. We're going to use the calculator after we've set up the integral. Again, this is easier without calculus than with. What's the name of that shape? Or it's half of a cylinder, right? So, and there's an easy formula for the volume of a cylinder, which you could cut in half. But let's see if we can use calculus to get there instead. What we're going to do is we're going to take this half cylinder, we're going to slice it into slabs here. I'm still going to call it slice, but in this case, it's that thing that's chunked out in the middle, the cut out sort of floating piece in the middle. This way. Can you come up here and draw something for me?
Well, wouldn't it be easier to calculate if you're going along like that?
So what do you? So you're saying?
Yeah.
So you're just making the shape thinner,
Yeah.
right? Yeah. So if you happen to know the volume of that thinner version, then we probably would use that formula for the whole thing. Yeah, I like the idea. All right. Volume of one slice. Okay, so that slice right there, ignore the fact that it is slightly curvy. Ignore the fact that it is slightly curvy, but would you guys buy that that is pretty much a shoebox shape, kind of a flattened shoebox? If you ignore the curves are not that great, and they would become even less if we made this slice thinner. But I'm just imagining, you know, like flattening out on the four corners there, and it's basically just a very thin shoebox, yeah? The difference between the distance here and the distance here is not all that great, especially if we make it thinner. It's bigger so we can see it right now. But if we make this really thin, I can approximate that thing by a rectangular solid shoebox, just like we used a rectangle up above. So imagining that that is just a box, what's the formula for the volume of a box? Yeah, that's our known formula, right? It's just the 3D analog of a rectangle. Okay, so let's start filling these guys in here. Okay, so let's do some stuff here. So I'm going to label these guys. I'm going to call. What do I want to do here? we'll call this guy right here, can we call that the width? Is that all right? And then the height is from here to here. And then I'm not going to label it permanently, but that's my length, okay? We've got our 3 dimensions labeled. Okay, so let's start replacing. The width is constant, right? It's always 10. And you got to imagine taking that slab and moving it up and down, and make sure you really believe that that width stays 10 the whole time. So this middle guy is definitely a 10. The H is symbolized in this picture. What is it? It's a delta Y, right? That's the height. We're holding it constant as we sweep this thing up and down. The length is the part that's tricky, because as you move this thing up and down, what happens to the length? It changes, right? Like, I mean, at the bottom, the length is, I don't know, 14. And at the top, the length is 0. And we need to come up with a precise way to decide by how it changes as you sweep that thing up and down. I'm going to give it a different letter here. Let's call this guy here X. I'm just going to call halfway because I'm going to draw something. I'm going to use another color. So that one right there we called X. I'm going to draw straight down to here, and I'm going to connect up to there. There's blue on, oh, blue on green is no good. Sorry. How's red? X. Down there, down there. Aha. Okay, so what's a good letter for this vertical? It's already on the board. That's what we called Y, right? How long is the hypotenuse? It is the square root of x squared plus y squared. What else is it? It's also 7. Yes? That is the radius of our cylinder, which is 7 all the time. Even if that slab moves up or down, that hypotenuse is 7. And so I'm going to come up here. I'm going to use a letter that I don't really want to use, but then we'll change it. The length, what is the length of the slab? 2x, right? 2x is the length. But as we said, what's the letter that needs to be the only letter in this expression? Is the y. It's got to be the thing next to the delta. So our job is to change that x into something with y's. Pythagorean theorem is the way we're going to get it. So as you said, x squared plus y squared is definitely 7 squared. What letter am I solving for? X, because I want to get rid of the x. So x is the square root of 49 minus y squared. And so that comes right back up here. Everybody see where the pieces came from? Okay. So our next line is the volume of all the slices or the slabs. And it's really just a matter of copying all of that stuff and what's our symbol for add up all the things that look like that? Sigma, right? It's going to be an integral in our next line. So right here, it's just a straight add up the pieces. I will put not an optional red I over there, except that's not where it goes. Optional red I on that guy. Just imagining enumerating the slabs. Slab 1, slab 2, slab 3 as I go up the chain. And then we say, hey, wouldn't it be great if we did this in a limit and we just changed it to an integral? So let's do that now. Not even going to write the limit. The summation becomes integral. Copying most of this stuff, 49 minus y squared. That optional I just disappears. Delta y changes to dy. And then the last thing to do, this is kind of my favorite part to visualize, is imagine taking that slice and moving it in the y direction. That variable right there is the direction that we are going. You are changing y and you are taking that slice and moving it up and down in this picture, how much is y at the bottom slice? 0. And how much is y for the very top slice is 7. So those are our limits. 0 to 7. Yeah, you could take the 10 out. What else could you take out? 2. So I'd put a 20 in the front of this guy. Now it turns out we actually could find an antiderivative of this by hand. Anybody remember or recognize the technique here? Trig sub, right? That 49 minus y squared is kind of the giveaway that maybe this is going to be a trig sub. So a trig sub will work, but we're just going to save some time here and type it in. So I've got a 20 and then integral, what are we doing here? Square root of 49 minus, I'm just going to do x squared, comma x, comma 0, comma 7. Did I type that right? Hey, that's a little shortcut. You got that here. XX. That's all kinds of fancy. Actually couldn't be any less fancy, really. Okay, so that's that, but we said we actually could do this one exactly. What's the formula for the volume of a cylinder? Pi r squared times the height. So the r here is 7, right? So pi 7 squared. See, my technique doesn't work here. If I do 7, 7, it's no good. It's only, times what's the height here? Times 10. But that would be if it were a full cylinder, so half. Do that right? Yeah. You could. This is not a time saver. Because the calculator is literally doing things like slicing up with rectangles and approximating with rectangles, and it's usually gives enough rectangles for our accuracy purposes. The bottom answer is closer to the right one. Yeah. All right. So that is good. Next page. Number 5. This next problem is concerned with finding the volume of a solid with known cross-section. That phrase right there is one that you will see several times. Warning, cross-sectional volume problems are typically harder than the ones that we just did. Let's give this a shot. We're going to find the volume of the solid, whose base is the region inside of the circle x squared plus y squared equals 4, and whose cross-sections perpendicular to the x-axis are squares. So our first task is to try to draw this creature. I'm going to do my best, and then we're going to use technology to see a prettier picture than I can draw. Don't copy this. X squared plus y squared equals 4, circle centered at 2, all right? But I've got cross sections perpendicular to the x-axis, which is coming out of the board this way at you, and it's really hard for me to draw stuff coming out of the board from this perspective. So you're going to use your imagination, and you're going to imagine drawing the x and y axes horizontally for the x and then kind of fading off into the distance for the y. So I'm just trying to push the y-axis down so that I can draw stuff coming up off of it. Okay, so there we've got our circle of radius 2. You can draw that. And now we're going to draw some squares perpendicular to the x-axis. For example, suppose that you have a square. I'm going to draw another circle. Okay, so suppose that you have this particular cross-section perpendicular to the x-axis there, and you imagine now a square coming off of the xy plane, coming up out of the board towards us a little bit, there, and there, something like that. That is one square. I'm going to draw another square that's a little bit to the right of that one. If you draw a square with that base, is it going to be smaller or bigger than the first square? Bigger, so it is going to come out of the board more, come off of the xy plane more. The idea here is that it has to be a square, and so as soon as you have the length of the base, the rest of the dimensions are determined. They're all the same, right? Where's the biggest square? It's right on the y-axis, right in the middle, right? And I'll draw one more. I'll draw a cute little one over here on the far right. Tiny square, because it's a tiny cross-section in the base. Something like that. But you imagine all of these things drawn, infinitely many of them, and you've got a volume, a 3D solid. Chris? Because it's a square. Yeah. Okay. All right. So you imagine drawing this thing. Now this thing, even though it's made of squares, which I would say are very pointy, and this thing is pretty smooth and curvy. I don't know if you can imagine more than just the three things that I've drawn there, but I'll show you another Mathematica player thing. Here it is. So you can see the cross-sectional squares there, right? And you can see it is a fairly round shape. There's our base, is the circle. And you just have these kind of two hard lines, or I guess they're curves, but these two sort of hard edges where the corners of the tops of the squares are connected. But everything else is pretty darn curvy. Buying it? So we're going to find the volume of this guy. Anybody know a formula for the volume of this particular shape? Me neither, right? So not everything is triangles and cylinders like the first two examples that we did. But the techniques that we have built up in the last two examples will give us a way to find the volume of this thing. So let's start. How do we start? Volume of one slice. One of those, not quite one of the squares. You've got to imagine, I'm not going to draw anything else in that picture, but imagine taking that blue square and just giving it a little bit of thickness, right? Just jiggle it a little bit left or right so it has a tiny bit of thickness, okay? So now it's, again, like a flattened shoebox. So it's got a volume. Let's start writing some symbols here. So we know that, again, the formula for the volume of a shoebox is length times width times height equals. Okay, the height of the shoebox, again, I'm not drawing it, but you got to imagine this blue thing has a little thickness. What would be a good symbol for the thickness of that shoebox? Delta X. I really like using X because it is sitting on the X-axis, right? That's the direction. So let's call that guy delta X. Now, in terms of the length and the width, well, the length and the width of my shoebox are just whatever the sides of the square are, right? And so let's see if we can kind of give a good name to the sides of the shoebox here. You could call them Y if you wanted to, because we've already got X built into the problem. But I'm not a fan of calling them Y. If you're going to call something Y, like just think about this point right here that lives on the circle. And we're very comfortable calling that X comma Y, yes? If we're calling that X comma Y, and how long is the blue side of the square? It's 2Y. Because Y, by definition, is from the X-axis to the point. So if you're going to call something Y, you better call it that. So the length of the square, the entire blue side, is a 2Y. And therefore the width or the height of the square is what? Also 2Y. Once you got it written down, it's pretty straightforward. The rest of this problem is going to be fairly routine, but just getting those two Y's written down is a big piece of this puzzle. Okay, so you got to be comfortable enough with the notation. This isn't like me being picky with notation. This is like you choosing your letters wisely and taking advantage of the fact that we know Y represents just that red thing over there. And so 2Y is the entire side of the square. Okay, so let's clean this up a tiny bit. So this becomes 4Y squared delta X. What letter do we want in this expression? Only X, only that guy. So we got to get rid of that Y. So we need a relationship between X and Y. It's in the problem. Do you see it? It is a square and they are the same, which we've captured up there with the 2Y, 2Y. But do you guys see an equation relating X and Y in the problem? It's X squared plus Y squared equals 4, right? That's the equation. That's the relationship. We don't need to create it with similar triangles. We don't need to create it with the Pythagorean theorem. It's there. So let's take this equation here and solve for which letter? Trying to solve for Y to get rid of the Y, right? So Y squared is equal to 4 minus X squared. You're welcome to take the square root of both sides. I'm going to stop here because actually I don't just have a Y in my expression. What do I have? Y squared. I'm happy. I've got it. So we're just going to change it right now into 4 minus X squared. So this becomes 4 times 4 minus X squared. Questions on that substitution? Okay, so let's finish up now. So that's the volume of one slice. So the volume of all the slices is just the summation of those kinds of things. Again, anything in red here is optional, so there's my optional I. And then right away, we'll just convert into an integral. So summation becomes integral 4 minus x squared. Delta x changes to dx. Yeah, you could pull the 4 out. Before we do any integrating, let's find our limits here. Focusing again on that highlighted x, the thing that was following the delta. That tells you the direction that you are sweeping. So we are sweeping left to right in that picture. 0 to 2? Negative 2 to 2, right? Whole thing. So you imagine taking any of these squares and just sweeping them left to right. At the far left, they're small, bigger, bigger, bigger until the middle, smaller, smaller, smaller until the end. Negative 2 to 2 are the limits. The letter following the D, which was the letter following the delta. So X is the direction that you are sweeping. Yeah. Okay, so for 0 to 4, I think would leave this circle.
Well, I'm talking about in terms of the, yeah.
Yeah, if you're gonna shift the circle, then the x squared plus y squared equation changes. That guy's centered at the origin. Yeah. Okay. So as Ben says, we pull the 4 out. We'll do our integral. So what do we get here? 4x minus x cubed over 3, which boggles my mind, by the way, that crazy shape leads to an integral. It's a piece of cake, right? Like this is one of the, like this could have been one of the first antiderivative problems you ever did. Like that's the level of difficulty of the integral from that wild shape that we have no formula that we've memorized. Okay, so we're plugging in. When we plug in 2, what do we get? 8 minus 8/3. I'll just write it. 8 minus 8/3. Minus, and then we plug in negative 2. That's, what did I do wrong? No, it's okay. Negative 8 there. Plus that. Okay, anybody have a final? We got here 16, 32/3, 128/3. Am I anywhere close? That's a negative 8 plus 8/3, yeah. All right, I'm going out on a limb. Somebody help me out. It got kind of fuzzy for me at the end. All right, so while folks are verifying or correcting my fraction there, I'm going to show you something else. Here we go. So here's going to be the same problem, but just another visualization. So this is one of my favorite parts. I'm going to push this button. Everybody looking? So this is the part where we take the y-axis and flatten it out so that we can see what's going on. Okay, now we're going to sweep one square left to right. There it is, sweeping out, sweep, sweep, sweep. And I really like that it's got all these numbers here. If you are at x equals negative 0.3, the area of that square is 15.6. If you give that square a little bit of a thickness, then the volume is 15.6 times the thickness, times delta x. And literally, it's a matter of thinking about adding up all of these individual areas times that little tiny thickness, right? So that guy sweeps left to right. And then finally, if we actually hold on to the traces, then we see the solid being built. And this is really how I imagine it being built. It's just sweeping left to right. Okay, it's that, or approximately that. Am I close? Did I get it? 128/3. Hey, that sounds reasonable. Okay, so that right there is 128/3, or about 42.67. Okay. All right. So there's kind of a we'll just end here on number 7. The procedure is here in number 8. You can read it later on. But what we've essentially just done is proven a formula, is that if you happen to have one of these cross-section problems where the shape of every cross-section has an area that you can calculate, if the area of the cross-section at X, if you have a formula for that, like we had our formula was this guy. That right there was the formula for the area at X, yes? Like at a particular X, that was our formula for the area of the square. So if you happen to have one of those guys, then ultimately, where did that formula end up going? This thing right here, whoa, this thing right here just ended up in an integral, right? I mean, it just got copied and pasted into that integral. And so if you happen to have an area formula, if you throw it into an integral, it gives you the volume of that solid. And that's what this formula says in 7 here. So that if you know the area formula is A of X for any X, then the volume of the solid is just the integral of that A of X. Mario. It's just our way of enumerating the actual squares. So I could call the red one X1 and the green one X2 and X3 and X4. Otherwise, it doesn't really make sense to add these guys up. But like without the I, it's just adding up a bunch of kind of generic X things. So it's just numbering them, just like we numbered our rectangles. Typically, you just start at 1 and go up to some n, and yeah, just starting. Yeah. Okay, so activities start on the next page. Let's see how far we can get. If you have old homework, go ahead and take it out for me. I'll walk around and check.